So, in this module we will be discussing the steady state sinusoidal response of transmission lines. We have derived the wave equations for transmission lines and actually saw that voltage and currents on the transmission line are more like waves, they actually propagate as waves. Okay. And we will consider sinusoidal response much as the same case as we considered the sinusoidal response for plane waves, because because the transmission line equations are linear, if I know how the transmission line would respond for a time harmonic or a sinusoidal signal, then any other waveform can be expressed as a Fourier series of consisting of these different sinusoidal signals, and therefore I can easily obtain the response of for any other waveform. Okay. So, this is in the frequency domain that we are going to consider. We will be talking about one sinusoidal excitation of the transmission line, and then let us see how such time harmonic or sinusoidal voltages and currents propagate on a transmission line. Now, before we do that, we need to very briefly review the concept of a phasor, because that is what we will be using in our transmission line equations further. If you recall, a phasor was basically a shorthand way of expressing voltage or a current without really specifying the frequency, because we assume that a particular frequency has been chosen, and for that frequency we do not want to always carry this cos omega t or omega t term. Therefore, this is a convenient way of representing those voltages and currents of the same frequency by dropping that omega t term, like we will see how it is done. So, given a voltage on the transmission line at any point z on the transmission line and a function of time of a particular frequency as cos omega t minus kz, we can actually rewrite this one in terms of the complex notation as V0, or rather real part of V0 e power j omega t minus kz, right. V0 we will assume to be real, and then we have a shorthand notation which we call as phasor, and this phasor drops the term for e power j omega t as well as this real part. Okay. So, the phasor for this one is basically the amplitude. In this case, the amplitude is actually changing with z, that is along the transmission line, and therefore your phasors are complex numbers which are functions of z as well. Now, how do you go from this phasor back to the original notation? Well, all you have to do is to multiply by e power j omega t and then take the real part of it, right. So, when you multiply this one by e power j omega t, you will see that this would be V0 e power j omega t minus kz, and then you take the real part of this to obtain the real time dependent voltage. Okay. So, this is all about phasors, and we will be talking about this voltage. Similarly, one can introduce a current phasor, and all our further equations will be described in terms of these phasors. Okay. So, the first step in order to obtain the sinusoidal response of the transmission line would be to actually rephrase the equations in terms of these phasors and then solve those equations. Okay. So, we will do that one. So, in order to do that, let us actually start by recalling what the wave equation was. So, del V by del Z was equal to minus R I of t. So, this is the case where you had both z and t, and this is in the time domain waveform I am writing, minus L del I by del t. This is what we had, but with phasors what happens is that this operation of del by del t can be replaced by multiplication by j omega, and the operation with respect to an integration can be replaced by 1 by j omega. Okay. So, with these substitutions in mind and then replacing this v of t by the corresponding phasors, what we get is an equation which states dv of z by dz is equal to minus r plus j omega l into I of z. Please note that this v of z is the phasor. Of course, in this case it is not I, it is just I of zt. Similarly, it is I of zt here and v of zt. These are the real time expressions for voltage and currents. Okay. But when we go to the phasor notation, right, when we employ the phasor notation, all the time dependent terms drop out, because we are assuming that all the voltage and currents on the transmission line are varying with a particular frequency omega, and then we use this phasor form to drop this omega t dependence. Okay. And del by del t will be replaced by j omega, and this is the first order partial differential, or rather in this case full differential equation that you are going to get which describes how the phasor voltage changes along the transmission line. A similar equation can be written for the current phasor, which is di of z by dz given by minus g plus j omega c, okay, times V of z. Hopefully this makes sense, because this is conductance times voltage must give you the current, and then j omega c into V is nothing but c into del V by del t, which would essentially be the current through the transmission line. So these are the two coupled first order differential equations. In order to solve them analytically, what we do is we differentiate this equation once more with respect to z, and then employ the second equation. So we differentiate equation 1, use equation 2 to obtain a second order differential equation for the phasor voltage, and that is given by minus r plus j omega L g plus j omega c into V of z. There is a convenient shorthand notation for this one. Okay, we call this is the most popular symbol that we use. This shorthand notation says that this is some complex gamma, and this gamma square is equal to r plus j omega L into g plus j omega c times V of z. Clearly this second order differential equation has a solution which will be consisting of both forward going wave as well as backward going wave, right. So for the forward going wave you have V0 plus e power minus gamma z, and for the backward propagating wave you have V0 minus e power plus gamma z. So this is my forward wave and this is my backward travelling wave. So what is gamma? Gamma is the complex propagation constant, although this is not really a constant. So maybe a better term would have been to use propagation term, and this gamma is given by square root of r plus j omega L into g plus j omega c, clearly because gamma square is this quantity r plus j omega L into g plus j omega c. So taking the root will give you gamma, right, and this inside will be a complex number, and square root of that complex number will also be a complex number. Therefore we can write gamma in general as two terms, real part as well as imaginary part. So alpha being the real part of gamma and beta being the imaginary part of gamma. These are called as attenuation coefficients or attenuation constant sometime, although again this constant is not really constant because it depends on the particular frequency that you are looking at. And similarly you have a phase coefficient. Okay, I choose to call them as coefficients because these are just coefficients, or phase terms would probably have been better fit over here. The idea is that these are functions of frequency and we need to express that particular thing. Okay, there are some cases where it won't be a function of frequency, then we will be talking about those things as special cases. Okay, the bottom line here is that we were able to obtain a second order differential equation, which is equation 3 over here, for the propagation of the voltage phasor. We solved that equation and saw that there would be forward as well as backward waves. Of course, we have not mentioned how the backward waves could be generated. That is something that we are going to do very soon. Okay, so let's for now assume that there is only forward going wave. Okay, so let's assume that only forward going wave is there, which means that the voltage phasor is V0 plus e power minus gamma z, and then differentiating this voltage phasor and equating it to the current term, what you get is minus r plus j omega L into I of z. So this equation, when you differentiate this V of z with respect to dz, will give you minus gamma V0 plus e power minus gamma z. Clearly what we have is I of z being given by minus gamma, or rather because minus on both sides will cancel, you have gamma by r plus j omega L into the phasor V of z, because this is nothing but voltage phasor. Now if you take the ratio of voltage phasor to current phasor and recognize that the voltage phasor has an amplitude V0 plus and the current phasor could similarly have an amplitude of I0 plus, okay, and the same e power minus gamma z kind of propagation, what you are really looking at is the amplitude ratios of forward going wave. Okay, this is very crucial, amplitude ratios of only forward going wave, and that ratio can be seen to be r plus j omega L by gamma. But I already know what is gamma. Gamma is nothing but r plus j omega L into g plus j omega c. Therefore, the ratio of V0 plus to I0 plus, which is the ratio of forward going voltage amplitude to the forward going current amplitude, is given by, this has to have units of impedance because this is voltage by current, and this impedance is a characteristic of the line because it depends on the parameters R, L, G and C, which further depend on the geometry of the transmission line, right, because L for a coaxial cable is different and L for a two wire line is different. C for a coaxial cable is different, C for a two wire line is different, which is again different from a microstrip line. Okay. So, this ratio is called as characteristic impedance. Okay. Although in this case this is impedance, for lossless line this becomes characteristic resistance. Okay. We will see that one very shortly. And what is this Z0? This is R plus j omega L by gamma, right. But substituting for gamma as square root of R plus j omega L into G plus j omega C will give you this expression. Okay. This expression is very important, and in general it describes the fact that V0 plus and I0 plus are not in phase, which means that not the entire available voltage and current is contributing to the power, some power is actually getting lost. Obviously that power must be getting lost in R and G terms, because R represents the imperfect conductors which make up the transmission line conductors, and G represents the imperfect dielectric that fills the conducting region. Okay. So, this is your characteristic impedance. Immediately one can identify different cases. Okay. So, let us consider the case which we call as lossless case. Okay. In the lossless case, we assume that the conductors are perfect, which means that there is no drop or resistance in the conducting wires and R is equal to 0. Similarly, we will assume that the dielectric that fills the conducting surfaces is also completely ideal, which means that there is no leakage or conduction current through that. So, G is also equal to 0. Substituting this, what do you get for gamma? Gamma will be j omega square root LC. Okay. And this j omega square root LC means that there is only phase term, with beta being omega into square root LC. Okay. What happens to Z0, the characteristic impedance? Well, characteristic impedance becomes square root of L by C, and this is completely real, which means that this is exactly like a resistance. Okay. So, if this is resistance, then there will be power dissipation, and that actually brings us to a nice paradox, right. We said that this is a lossless case, but then we saw that the characteristic impedance turns out to be like a resistor, right. So, if for example this is your V0 plus and there is a current I0 plus, the equivalent transmission line thing would actually look as a resistor square root L by C. But we know that a resistor dissipates, is a passive device which basically dissipates energy, correct, energy or power, it dissipates energy. But if a line is dissipating energy, then why do we call it as a lossless case? Is there a paradox somewhere over here? How can a lossless line be equivalent to a, this is the equivalent of a transmission line, right? How can a lossless line be equivalent to a resistor? This paradox, if you think about it carefully, actually can be resolved in many ways, but two ways one has to understand. For now, we are considering only forward going waves, which means that there is no end to the line was actually infinite, right. So, line was actually infinite in length, or it was matched with Z0, we will come to matching thing later. For now, we will assume that this line is infinite in length, and for an infinite length, if the voltage source connected at the input terminals of the transmission line generates a certain current and therefore puts out a certain amount of energy into the line, that energy keeps propagating, it would never come back to the source, right. So, it is as though the transmission line acts like a black hole, right, sucking up all the energy and returning nothing. So, in terms of this is clearly, in terms of the source, it is clearly a lossy transmission line, because source has put out energy, but that energy is not coming back to us. Well, technically the energy would be coming back to us, because it goes all the way to infinity. Only thing, you have to wait for an infinite time, which is practically saying that that amount of energy is simply lost on the transmission line. Okay. And that is what is captured by having a real resistance as an equivalent resistance for the transmission line. Now, if you are not convinced with this solution, try this. Actually, a lossless line would if you go back to the sectioning of a transmission line that we did, would consist entirely of L and C, right. So, this is how an equivalent transmission line circuit would look for the case of a lossless transmission line. And what you see here, you will see some inductance per meters, capacitance per meters, but these inductances and capacitances are precisely energy storing elements, right. So, which means that whatever the energy that is given to the transmission lines, okay, by the source, okay. So, if you connect a source and put out some energy, that energy actually goes in the form of storage, okay. So, the lossless line actually simply starts storing the energy rather than dissipating that energy. So, again from the source point of view, this kind of energy is lost on the transmission line, but energy is not really lost in the sense because energy is getting stored in the transmission line, okay. Now, this equivalent circuit also must tell you why there should be a delay between voltage at this point and voltage at this point, okay. Why should there be a delay? If you hook up an oscilloscope over here, okay, and then see what you actually get. So, if for example this is the voltage waveform and then you hook up an oscilloscope here, you would see that the voltage waveform would actually be delayed, right. This delay is now, or this delay can be explained qualitatively because the equivalent circuit of a transmission line consists of L and C's, right, which means that there has to be some current for charging the inductor and some voltage across the capacitor for charging the capacitor, and this current has to flow, charge the inductor, charge the capacitor, then this has to flow, charge the inductor, charge the capacitor, and so on. Because of this charging process which takes time, there will be some amount of delay in the voltage at two different points on the transmission line, okay. Now that we have seen this lossless case, let us look for a slightly more realistic case, okay. In the realistic case, what we have is omega, the operating frequency is so large that the term omega L is much larger than R, and similarly the term omega C is much larger than G. In this case, what happens? Gamma will be approximately j omega square root L C and Z0 will be approximately square root of L by C, okay. So, this case, which we can call it as high frequency case, okay, is almost similar to that of a lossless case. In the lossless case, there was only propagation, no attenuation, the characteristic impedance was real, and the same thing continues for high frequency line also. In practice, you do not really get such nice high frequency lines, or although you do get high frequency lines, you cannot completely ignore R and G, but there is another kind of condition which is called as Heaviside's condition, and this case is slightly interesting because in this case you actually adjust the transmission line parameters in such a way that L by R will be equal to C by G. Do you recall what L by R is? L by R is the time constant for a RL circuit, right. So, for an RL circuit, the charging time is characterized by the time constant L by R, and similarly for a capacitive circuit, the charging time is characterized by C by G, and 1 by G is kind of R, therefore, this is RC time constant. So, what we are saying is series time constant, okay, must be equal to parallel time constant, okay, where this parallel is simply indicates that this is capacitor and a conductor, okay. So, if these two time constants are actually equal, then this case is called as distortionless case and the line is called as distortionless line. What do we mean by this is that if you launch a particular waveform on the transmission line, okay, at say z equal to 0, which corresponds to your source, at z equal to L, which corresponds to your load, okay, the waveform would be delayed, of course, because it is a transmission line. So, it gets delayed and then its amplitude might also decay, okay, indicating that the attenuation is not 0, but the waveform actually would be the same. So, you can see some delay, you can see some amplitude loss, but you will see that the waveform actually has not changed its shape. So, whatever the waveform that you have put out at the load, the same waveform shape would be available at the load as well, okay. For this particular case, I will leave it as an exercise. You can show that gamma will consist of both alpha as well as beta, and we are interested in what is alpha. So gamma is alpha plus j beta, where alpha can be shown to be equal to r square root of c by L or g square root of L by c. Okay. Similarly, you can show that z0 for this case is approximately square root of L by c, and this is again real. Okay. There is one last thing which I want to discuss before we go to the next topic at hand, and this is called phase velocity. Remember, our waves are going as V0 plus cos omega t minus beta z, assuming that this is on a lossless line, alpha is equal to 0. So this is how the voltage actually propagates on the transmission line. Now if you pick a particular point which is characterized by having a constant argument, that is omega t minus beta z is equal to some constant, right. So you have your waves which are going as a cos omega t, right. So you have this wave, and if you pick a particular point, okay, which is characterized by, so this has to be both z and t, I am just showing it as a function of z. So if you pick a particular point at which this argument omega t minus beta z is constant, and then look at how this particular constant point actually moves in time, then the velocity with which it moves will give you the phase velocity, because this would be the phase with respect to some reference phase, and what you are looking at is how this phase itself is changing, okay, as t and z increases. To obtain the expression for phase velocity, you can simply differentiate this one with respect to time, and you get omega minus beta dz by dt. Beta is assumed to be independent of time, so this would be equal to 0, and this dz by dt is the velocity of this constant point. So this velocity is denoted by up, and up is given by omega by beta, because this is nothing but omega minus beta up equal to 0. So you can push this on to the right hand side and then interchange the left and right hand side to see that up is equal to omega by beta. For a lossless case, we have already seen that beta is nothing but omega square root LC. So which means that up, the phase velocity, is given by 1 by square root LC. Okay. And this is again the characteristic of lossless line, low loss line, or the high frequency line, as well as for the distortionless line. Okay. Why for the distortionless line? Because in the distortionless line what you have is beta being some constant omega times something. Okay. So it would actually be again real, and this is the reason why you actually have no distortions. If your phase velocity would start to depend on omega, then there would be distortion, something that we will come back to the scenario later, okay, when we discuss group velocity. Okay. We talked about attenuation, right. So we said that attenuation is nothing but loss of amplitude, okay, loss of voltage amplitude or current amplitude, and then if attenuation, which is defined by alpha or which is denoted by alpha, is non-zero, then the voltage phasor V of z goes as, assuming again only forward going wave, you have V0 plus e power minus gamma z is a general voltage phasor on the transmission line. This becomes V0 plus e power minus alpha z e power minus j beta z. Suppose you are interested in finding out the magnitude of V of z, this magnitude will be equal to V0 plus e to the power minus alpha z, and you can see that this magnitude actually decays with a decay constant of alpha, right, or 1 by alpha. The slope is 1 by alpha, and as the wave propagates along the transmission line, its amplitude starts to decay. Okay. We sometimes are interested in finding out what is the loss per unit length. Per unit length would be denoted by per meter, and the loss is typically talked about in terms of dB or units of decibel. Okay. So what is this decibel loss per meter? Decibel loss per meter is simply minus 20 log to the base 10. What is the input voltage that we gave? V of z equal to 0 divided by V of z equal to 1 meter. Okay. So this is what we mean when we say that this is dB loss per meter. Clearly, if the transmission line is lossy, the voltage that we give at V at z equal to 0 will be greater than the voltage at z equal to 1. because this numerator is greater than denominator, this would represent the loss. Why should it be greater? Because V of z equal to 1 magnitude will actually be equal to V of z equal to 0 times e power minus alpha, because you have propagated z equal to 1 meter. Okay. So therefore, you have the voltage at a later point in the transmission line to be less than what is the input voltage, and that ratio is characterized by dB loss per meter. Okay. Now you substitute for V of z equal to 1 and evaluate this expression. What you get is minus 20 log of 10. V of z equal to 0 is simply V of z equal to 0. Okay, it could be V0 plus, and then what you get is e to the power minus alpha. Now you can rearrange this one, or you can take the log to this thing. What you get is 20 alpha into 20 log 10 to the log to the base 10 times e, but this log 10 to base e is nothing but 0.434. You can check the log tables, and what you see is that alpha, that loss, dB loss in meters, is actually given by 8.686 times alpha. Okay. If I call this one as alpha dB per meter, okay, and then this alpha, which is coming from the actual expression of e power minus alpha, will be denoted by Nepper per meter. Nepper is a dimensionless unit, so this is Nepper per meter, and this is the relationship between dB per meter, loss of the signals in dB per meter, to loss of signals in the natural units Nepper per meter. Okay. So it is worthwhile to represent these equations. So I mean highlight this equation. So I am going to write this again. Alpha in dB per meter is 8.686 alpha in Nepper per meter, and you can actually interchange this equation also. And if you know what is alpha in Nepper per meter, you can write down what is this. This would be around 0.11, okay, times, because it would be 1 by 8.686, so it is approximately 0.115 something times alpha in decibel per meter. Okay. So given one alpha, you can convert that into the second alpha. Let us try out an example, okay, to just show you what attenuation things can do. Let us try out an example. Let us assume that voltage at z equal to 0 at the input terminals is 7 volts. What we want is voltage at z equal to 10 meter. Okay. Given that alpha is 0.5 dB per meter. Okay. So the loss is actually 0.5 dB per meter. You can substitute for this 0.5 dB per meter loss, and then you can solve it in two ways. One, you can solve it in alpha in dB per meter itself, but in this case it probably is easier to first convert this into Nepper per meter. Okay. So you can consider this dB per meter, convert this into Nepper per meter. When you convert that, that would be 0.115 into 0.5, which is approximately 0.057, okay, Nepper per meter. And then voltage at z equal to 10 meters will be the voltage at the source side times e power minus alpha Nepper per meter into 10, because z is equal to 10, right. So you substitute this is 7 into e to the power minus 0.057 into 10, okay, and if you use your calculator, you will see that this is nothing but 3.94 volts. Okay. So you can see that the voltage at z equal to 10 meter, okay, has actually dropped from a value of 7 to 3.94 volts. Okay. So from 7 to 3.94 volt, it would continue to drop if the transmission line is actually extended beyond 10 meters.